told you, you know exactly when I start recording. Okay, so this section is called the idea of a limit. The idea of a limit. So I want to take you back to grade school. And I want to go back to that, is what I say if I, let's see if I can make a perfect circle. That's why. There we go. We got this nice circle. All right. This is why I like using a computer, because I can draw a nice circle. Let's go back to the circle. There are two things. There's lots of things you remember about a circle, I hope. You worked with radius and diameter and all that fun stuff, right? We also did two other things. One was called a secant, and the other is called a tangent. Now, we are not talking about trig functions right now. We're talking about lines on a circle. Can anyone tell me the difference when it comes to a circle between a secant and a tangent? Maybe you remember a tangent line to a circle. What does a tangent line to a circle do?
I think it's a line that sort of perfectly, say, merges into a circle.
So merges into like that?
No, like around the border.
Like that?
Yeah.
Okay. He's correct. That's a tangent line. What's a secant line? I already drew it as a hint. I already drew it. What's a secant line? Cole. Okay, that's a secant. And that's your tangent. So as we go through this section and understanding the idea of a limit, I'm going to use those words. So before I use those words, I need you to remember what they are. It's really important. The tangent line touches the circle just at a single point. Okay? Your secant line goes through 2 points of a circle. And a secant line that cuts a circle perfectly in half is your diameter. All right, so now you remember your secant, your tangent. All right, so that's kind of like a separate thing. So when I now use secant and tangent, you know what I'm talking about through the lesson. Now we're going to go to something else you know. And we're going to talk about, and it's a really important concept, and it's something we're going to use this idea of velocity throughout the course at various times to help showcase some concepts. And the one we're going to look at today that is going to help us understand limits, it's this idea of understanding the difference between an average velocity versus an instantaneous velocity. Didn't look right, but that is spelled right. Is anybody a really bad speller in here? Okay, I have a doctorate, and I'm a really bad speller. Just so don't feel too bad. Don't feel too bad. And then we're going to connect it back to, so think about what I just did. We did tangent and secant line. You're thinking, what does that have to do with an instant velocity versus an average velocity? So if you were to try to connect these two words with either tangent or secant, which one do you think will go with which? Secant average. Does that make sense? Instantaneous is tangent. That's correct. And that we'll get to that later in the lesson. So we're going to start with another thing that you've worked with. I like to try to build on stuff you've learned already. And we're going to do projectile motion. You've worked with projectile motion before. Parabolas, right? You've worked with parabolas before. So let's suppose that I want to point out what I do this all the time. I want to point out one thing. If you print out the notes from the class, my notes will mimic those, okay? So where in class, I might not write every word of the problem down, they're there online for you. Does that make sense? So what a lot of students will start doing is taking those notes and bringing them to class, because then you're not copying everything, right? So just to kind of let you know. So let's suppose we have a rocket. All right, it's on the, I'm not even going to try to draw the picture. It's on the ground. It's launched vertically from a ground speed of 96 feet per second. So I don't know if you're familiar. I'm not a physics teacher, but anything with projectile motion follows a certain pattern. And one of the important pieces of information is gravity, right? And initial velocity when we put this together. So if we are going with an initial speed of 96, so it kind of looks like this. We have something called our position function. Throughout this course, our position function is always going to be called S sub t. As we progress in the course, we're going to get a velocity function, we're going to get an acceleration function, but today we're just going to talk about the position function. The position function will give you the position, that's your S, at a specific time, that's your T. So think of, and we're going to graph it in a second. So this particular rocket, first, so this is what the equation looks like, and we'll go through each piece of it, plus. So why does our position function for this particular rocket look like this? That negative 16 comes from gravity. All right? The projectile motion, the position with projectile motion, it's always 1/2 of g. So gravity in feet, I believe this problem is feet per second, is 32 feet per second. The gravity on Earth. If we were on another planet, it'd be totally different. Okay? So that's where the negative, so that's pretty standard. Have you done these problems before and you always saw that negative 16 in the beginning? That's because it's standard for gravity. All right? It's your G-force. And it's always 1/2 gravity. If we were working in metric, it's like, I think we use like, I want to say it's like 9.6 or something like that if we're working in the metric system. Now, plus, this is considered V sub 0. In this course, whenever we talk sub-zero, does anybody know what sub-zero stands for in math and physics and everything else? Yes, initial. So that's our initial velocity. So if our initial velocity is 96 feet per second, that's where that piece comes from, 96 feet per second. So what gets taken into consideration? The initial force put on it, the gravity that's acting on it. What else would be taken into consideration? We talked initial force, talked gravity. What do you think else matters? Where it's starting. We're done with this one because we said this rocket is going to start on the ground. If we were starting the rocket on a 100-foot launch pad, we would have plus 100. All right? So projectile motion follows a very basic pattern. And again, not a physics teacher, but after you take Calc 1, how many of you are going to Analytical Physics 1 after this? A lot of students do. It's one of the first set of problems you'll work with. All right? And it's this idea, and it's usually negative 1/2 g t squared plus v sub 0 t plus h. Okay? So it's, you know, we try throughout the course to use real problems as much as I can without having extensive knowledge. I took physics in 1989. Okay? Not that it's really changed much. I took it in 1989. So there's my initial. So you're going to see this again. Various times we'll go back to this position, type of position function. This is only projectile motion. We can use position functions other ways that aren't projectile motion, and it's a t cubed problem or something like that. All right? All right. So now, what I want to do first is talk. Did you have a question? No. I want to talk average velocity. So again, we have time and we have position, we know. So where does velocity come from in any problem? Does anybody know? If we know how far it's gone, and we know the amount of time it took to get that far, how do we get velocity? Right? So think of rate. You all go back to something you know. Everybody remembers this because Algebra 2 loves Cole. So we all know this, right? Because in algebra, D equals rate times time. Remember that? You've used that before. You've seen that, D equals RT. Whoops. Hopefully you've used that before in like your algebra classes or basic physics classes. So we think of velocity as the rate. So yeah, that means rate equals distance traveled divided by time. So that's how we can use position function is going to give us how far it traveled. And of course the t is going to give us the time. So now what I want to do is say, hey, what is the average velocity oh, it's actually rock, not a rocket, but doesn't matter. I just looked, I said, oh, a rock's being launched. That's not exciting. Who launches a rock from the ground? Anyway, of the rock between, let's first do t equaling 1 and t equaling 3. All right, so now, graphs are helpful too, right? So again, this is projectile motion. We know at time 0 it's sitting on the ground, correct? The rock's going to, you know, as time, so time is across here, right? Position is across here. So as time goes by, this rocket's going to increase, correct? Until it's going to do what? This rock. It's going to stop. And then what's going to happen? Yeah, it's going to reach a max height, and then it's going to come down, correct? All right. So we need to figure out, hey, what was the average velocity between time 1 and time 3? Well, how are we going to do that? Well, what do we need to know? What's the position at time 1? That's why I told you guys to get the note to bring calculators. I don't bring calculators. I refer to my calculator if I can't get 3 people in class to agree to a number. Seriously. And then I have to get my calculator out and I can do the calculations. Yeah, I know I have the answers in front of me, but come on, this is a math class. Get your calculators out. So what do I want to do? First, I need to know, what is the position at time 1 and what is the position at time 3? So let's get those 2 numbers. So I need this value right here. In order to work on velocity, I need to know where it is after a second, and then I need to know where it is after 3 seconds. So what is the position at time 1? And again, you never let one person do the calculations. Anyone else? Do we agree? I knew she was right. But again, everybody's got to agree. 80. Yes. So S sub 1 equals 80. What's the position after 3 seconds? Well, we got to just find S sub 3. So you put in 3. 9 times angle 16. 144. Do we agree? So now I need to know average velocity. So to get average velocity, I can find red. We're going to use hot pink apparently. Average velocity is simply going to be the slope of the line that goes through those 2 points, which we now know is called a secant line. So to get your average velocity, I said we're going to go back to something, you're going to start with something you're very familiar with. All you're going to do is find the slope, right? Because slope is change in y over change in x. Change in y is the distance it traveled. Change in x is the time it took to travel that distance. It's just slope. All right, so let's find the slope between those 2 points. So my average velocity between those 2 points is simply going to be, all right, we can do it. So we're going to call it VAV. So it's average velocity. Okay, V sub AV is going to be, so how do I find slope? I take position first, 144, right? Minus 80 over, well, it's going to go in the denominator if I do 144 minus 80. 3 minus 1. So go ahead and get me that average velocity between 1 and 3. 32? Do we agree? 30? Awesome. It's going 32. And we're going to, I'm really, really bad at using the measurement. So let's remember to do that. You sometimes have to remind me. Because, yeah, I'll mark you wrong on a test, right? No. Well, yeah, I will. Feet per second. Okay. It's going 32 feet per second. Okay? You're like, all right, well, that's cool. That's easy enough. Can you tell me right now what the instantaneous velocity is going to be at exactly 1 second? And if you already took calculus and you used the word derivative, nope, I'm going to smack you. No, I'm not going to smack you. But not allowed to go there. And if you don't know what I'm talking about, perfect. Can you tell me the instantaneous velocity? What is the speed at exactly? So if you're driving a car, it's easy, right? If you're driving a car, what do you have in front of you? Your speedometer. That gives you instantaneous velocity. I could be driving here through the back roads, and at one point, like, all right, it's back roads. I drive a little fast. Oh my gosh, especially through Golden Valley. And I've only been stopped once. Luckily, it was a graduate of RVCC, so they let me go. Oh no, I stopped twice. That's okay. I might hit 55 miles an hour, right? At some point, maybe 60. As an instantaneous. Do you think my average velocity was 60? No. My average velocity coming to work might be 30. I'd have to figure out, I know I drive 38 miles. I know it takes me about 50 minutes. So do that for me real quick. 38 miles divided by, well, so I'm going to change 50. Oh, wow. That's miles, but it's okay. I'm going to change it to hours. So we'll say an hour. 38 miles an hour. Right? We'll keep it simple. We'll say 50 minutes is actually 60 minutes. So it takes me about, I drive on average 38 miles per hour. But at any given time, I'm doing all sorts of instantaneous velocities. Yeah. can you just calculate the instantaneous velocity? Not necessarily. That's what we're going to do. So now, you found it, the average velocity from 1 to 3 seconds. I want you to redo it, and I want you to find the average velocity between 1 and 2 seconds. So what does that mean? We're going to get a little bit closer. You already have S sub 1, so all you need to calculate is S sub 2 and redo the slope. You guys can go ahead and do that. I'm going to put a new tangent line in at 2. Just looking at the tangent line, it should be what? Faster or slower? What do you think? Right? If you're looking at that tangent line, it should be faster. So we were going 32 feet per second on average between, or the rocket, right, was going 32. Initially, though, as you get closer to 1, because think about it, that's the very beginning. The least amount of gravity there's been the least amount of gravitational force, right? Isn't it going faster in the beginning than as it moves up? So let's find that velocity. We'll do this one in bright blue, apparently. Can you see that blue? Here, you can see it. All right, so I'm no longer at 144 because 144 was S sub 3. I need S sub 2. What does S sub 2 give me? What is it? 240? Yeah, I was going to say, because if you look at the graph, it should be less than 144, right? This is between here and here. So what did you get? 128? So now our equation, our slope equation for the secant line becomes 128 minus the 80, because that initial didn't stop. We're still going from 1 second. But instead of 3 minus 1, I now have to do 2 minus 1. We think it should go faster. The average between the first and second should be faster than the average between the first and third. So what do we get for that average? 48. Right? 48. Yep. Okay. Well, am I not getting closer to what's happening at 1 second? Right? I'm closer than I was between 1 and 3, meaning the average velocity between 1 and 2 is certainly closer to the instantaneous of 1 than the average between 1 and 3 was. So now, how can I get even closer? I did between 1 and 3. I did between 1 and 2. 1 and 1.5. Sure. Okay, now we're using decimals. We're going to calculate one more, and then I'm going to give you the other numbers. Don't worry, I'm not going to make you do them all. As you can see, I will attempt to do another color. Green. We haven't done green yet. So between 1 and 1.5 is going to be even what? Should be even steeper, right? So V, this is going to be between 1 and 1.5. So I need someone to calculate for me S sub 1.5. S sub 1.5. It would go here. And here's the good news. When you go back and look at your notes, the publisher makes much prettier pictures than I do. So that's why they're also kind of good to have in front of you. Because mine starts to get a little sloppy. All right. So what's happening at S sub 1.5? 108. 108? We're good? So that's 108. So now it's 108 minus 80, 1.5 minus 1, correct? That looks good. So we were 32, 48. We should be even higher, correct? What do we get? 56, yep. How can we get even closer? Say it. Go for it. let's jump really close. 1 point. I'm not going to make you do any more calculations, okay? I promise. I'll give you the rest of the calculations. I'm not even going to attempt to draw it because it's just going to get too mushy. Does everybody see where we're going? So now, if I do, so let's do this. So let's make my time interval. Oh, let me go back to this blue. I'll include some of the ones we did. We did 1 to 2. And what do we get for average velocity between 1 and 2 was 32. 48, sorry. 48 was 1 and 2? Yeah. Okay, so we're going to make a little chart. Let's make a little chart. Between 1 and 1.5, we were at 56. If we were to do the same thing and only go to 1.1, again, I'm not going to make you do this math, we would actually be 62.4. Let's get closer. Let's go to 01. All right, now I'm going to pick numbers I already have calculated out, by the way. Let's go to 1.01. So you see what's happening. We're getting closer and closer to 1. Between 1 and 1.01, we're actually at 63.84. Do you see how it's slowing down? So that means we're getting close. We're not good enough yet. Let's go even further. Let's go between 1 and 1.001. We'll try to do a little pattern here. Now we're at, we're staying with 63. That's exciting. We're getting even closer. 984. Here's what I will tell you. As you are doing problems like this, you need to carry out some decimals. Rounding isn't going to help you. You'd be done. You'd be done if you were rounding, right? No, we got to carry out the decimals like 3 or 4 places sometimes. We're going to do just one more. So I got closer and closer and closer. And now I'm at, notice the number isn't changing much. 998. In fact, if we were to continue this, what do you think? Yeah. If we were to continue it, in other words, if I went to find, let me put my little equation back. All right, 1. And find the slope of the line at that point. So the instant velocity would be about 64 feet per second. Okay, your instant velocity at that point is 64 feet per second. That instant velocity, of course, is the slope, which is the slope of the tangent line. I think 80 was that position at 1 second, right? Okay. Would I get the same tangent, the same slope, if I did this tangent line at 2 seconds? Because as you draw, because actually, right here, what would the slope of your line be? 0. Because when it hits that point where it's about to turn around, the velocity is 0. Okay? And then, what happens to your slope after that? Yeah, it becomes negative because it's going downward, back toward the earth. So you'd have a negative velocity. So, understanding the difference between an average versus an instantaneous concept you need as we go through derivatives and integrals throughout this whole course. This brings us to the idea of a limit, because not once did we actually figure out what was happening at exactly 1, right? We figured out what was happening at 1.00001. We never found out what was happening exactly 1, but we got there by using a limit. Because we got, and that's the idea of a limit. It's figuring out what's happening at a point by looking at what happens as you approach that point. Okay? Now, when we do derivatives, you're going to find this in 2 seconds. That's what's awesome. You'll never have to do this because you're going to be able to use a derivative to get a slope of a line. All right? But before we get to there, we got to get through limits. And this kind of gives you that idea of how a limit works. All right? And I told you today's lesson would be short. All right? I know I have like an hour. I feel like I should teach more. No, you're good. So, you know, just getting that idea down that, and when, again, what I want to do now is kind of show you, and I'm going to turn the video off because this lesson, it's a short, very short. Everybody is capable of doing all the homework for 2.1, right? Between now and Tuesday, I hope. So let me show you